Okay, folks, so we've come to this portion of the course where we've been using our limit definition of the derivative to find derivatives. We've probably noticed that it is a little bit clunky. It takes a while. It's a lot of work to find derivatives that way. Luckily, we aren't the first people to have studied calculus in the world, right? So a lot of people have already done that work for us, and they've discovered, using that limit definition, some shortcuts and rules that are going to make our lives a lot easier. You will eventually have to memorize most of these, but for now we're just going to focus on learning how to use them, and you can look them up as you need them. Okay. Before we jump into this, I want to introduce another notation. So we already have our prime notation. So that notation is if f of x is the function, then f prime of x is the derivative. The other notation is, you see it down here, actually. They're both pretty intuitive. You'll learn to use both of them. They're useful for different reasons. So y would represent the function in that case, and then dy dx is the derivative. And you read it just like that, dy dx. Looks like a fraction. Sometimes it behaves like a fraction, but it's a derivative operator that represents the derivative. Okay, so these are equivalent. They mean the same things. Prime notation is useful when you want to emphasize the function. So maybe you have an f of x and a g of x that you're working with, and you want to keep them separate. This differential notation, dy dx, is useful when you want to emphasize the variables. So let's say we had y, and y depended on x and z, and we wanted to say we're interested in x and not z. That's why we'd use this one. In general, you want to stick with the notation that they give you, okay? So if I give you f of x, you're going to say f prime of x. If I give you y, you can either say y prime or this dy dx we're going to use more and more. The reason this is the case is some weird history. Essentially, calculus was invented independently at the same time by two different people, Newton and Leibniz, and they wrote things down different ways. And because they kind of invented these things at the same time, both their notations kind of stuck around. So prime notation is sort of an evolution of the notation that Newton used, and differential notation comes from Leibniz. There's a lot of interesting history. They kind of fought over who is the father of calculus. But because both of the notations here are useful, we're going to keep them both. All right. Let's jump into some rules here. So we'll do this in two parts. These are the sort of easier rules we'll start with, and then in the next part we'll tackle some more complicated ones. The first rule, these first two actually, we barely even need to call them rules. So the constant rule, the derivative of a constant, is always 0. Okay, so the way we write that down, so we'd say something like this. So this is a derivative operator that comes from this Leibniz notation. So d dx, the derivative of a constant, is 0. I'll say c is a constant. Constant, means just a plain old number. So we can go ahead and look at our examples here. 0, 0, 0. And then this is an interesting example. So even when your constant is a variable, so like this is something times pi. We know pi is a number. A here represents a constant, but we don't know what it is. This is still 0. Okay, so this constant rule is true even if we're just using a letter to stand in for a constant. They should tell you in examples like this, like a is a constant. This is consistent with what you already know, because you know that like a line like y equals 7, that's just a horizontal line. So this has 0 slope, and you know that the derivative is synonymous with slope, right? Single variable rules. Again, don't really even need a rule for this one. The rule here, though, is the derivative with respect to x of x. Well, if x is a variable, you know that the derivative is synonymous with slope. That derivative is 1. Okay? Because this function has a slope of 1. So 1, 1, y prime is equal to 1, f prime of x is equal to 1, s prime of t is equal to 1. Okay? It doesn't matter what the variable is as long as we're taking the derivative with respect to that variable. All right, here's the moment we've been waiting for. This power rule. So we have seen in a previous lesson that when we apply the limit definition here, we get 2x. We'd say y prime is 2x. I'm going to solve the other ones for you, and I bet you're going to notice the pattern. F prime of x for x to the 6th would be 6x to the 5th. S prime of t for t to the 30th would be 30t to the 29th. And then we'll talk about d here in a second. We'll talk about what the pattern here is. So what we're doing is we're multiplying by the exponent, and then we're subtracting 1 from that exponent, right? And obviously 2 minus 1 here is 1. So that's the power rule. The way I'm going to write this down in a general way, the derivative with respect to x of x to the n, so n is my power, equals n, so we multiply times the power, times x to the n minus 1. And this works even for fractions. So that's how we're going to do letter D here. Okay, so notice, or recall, you know this, the square root is the same as y equals x to the 1/2. So I can rewrite letter D, and then my derivative y prime, same rule, 1/2, so I'm multiplying times the power, times x, 1/2 minus 1, well 1 is 2/2, right? So that gives me negative 1/2. So there's my derivative for D. So the trick here is we can rewrite our exponents, or rewrite certain functions using these exponents, so we can use this power rule. You're going to come to know and love this one. Okay? We're going to use that same trick here. So you may remember that when we have fractions, I can switch which side of the fraction my variable is on, and then I can change the sign of the power. So this is really the same as 1x to the negative first. Probably learned that in algebra 2. Okay? And then my derivative y prime would be negative 1x, and then I subtract 1 from negative 1 to the negative 2. Same thing here. So f prime, well, let's go. F of x is x to the negative 3rd. So I'm rewriting it so I can use that rule, and then I get negative 3x to the negative 4th if I subtract 1. So that is the power rule. This is going to be the one I want you to focus on, because this is the only one that's not completely intuitive. I think the other ones are pretty obvious, right? And then the last complication we'll add before we move on is what's called the constant multiple rule. Okay? So that just means if I take the derivative of a function times a constant, that's the same as the constant times the derivative of the function. What does that mean, right? Make sure you give yourself some room here, because I want to make sure our work is clear. So for letter A, I can rewrite y like this. Y is really 2 times 1 over x squared, which is still 2 times x to the negative 2, right? So I pulled my 2 out, and then y prime is then just going to be 2, and then I'm going to follow my power rule. So I'm going to multiply by the exponent, negative 2, and then subtract 1 from it. And then I can just, as my last step, multiply those back together. So essentially what this rule is saying is that this constant in front of a function works exactly like you think it would. So for example, s prime of t for letter C, I'm going to use my power rule, 5t to the 4th, so I subtracted 1 from the exponent, multiplied by it, and then it was negative, it's still negative. So that negative 1 just comes down as I take the derivative. Now, f of x here, this one, same thing, even though it's a fraction, so 4/3 x to the 3rd, and then my derivative f prime of x, so 3x multiplied by my exponent, subtract 1 from it, and then 4/3 is just chilling. And then notice here they cancel out 3 and 3, so I'm left with 4x squared. Okay, so that's my constant multiple rule. Same thing here. So y is 4x to the 1/2 as I rewrite that like we did before. And eventually you're going to get to the point where you can kind of do this all in one step. So what I do in my head, and some of you probably can do this right off the bat, is I say, well, 1/2 times 4 is 2, and then x, and then I subtract 1 from it, negative 1/2. Okay, so I just kind of skip this step of writing the multiples separately. Okay, so that's your first four derivatives rules. Again, this constant multiple rule, exactly like you'd expect. These two rules, exactly like you'd expect. The power rule is the one you're going to be focusing on for now.